Hey everyone, and welcome to This Explainer, brought to you by Forge College. Today, we're taking a really fascinating look at the structural backbone of smart contracts. If you think of a smart contract as this highly automated, self-sustaining factory on the blockchain, well, today we're looking at the factory blueprints. Specifically, we'll be examining the individual machines on that factory floor, which we call functions, and the security guards that protect them, known as modifiers. It's an incredibly cool concept to unpack, and the way Solidity handles this architecture is just so elegant and highly practical. Now look, I know some of you might be feeling a little bit of whiplash right now. In our last lesson, we were deep in the weeds of practical error handling in Rust, dealing with some incredibly strict system-level architecture. But today, as part of our Solidity from Zero track, and specifically diving into control structures and functionality, we're switching gears. We're leaving the heavy, rigid systems of Rust behind for a moment and stepping into the highly structured, encapsulated world of Solidity blueprints. It's a bit of a mental shift, but honestly, a really fun one. Okay, let's dive right into the master schematic for today's factory build. First, we'll look at the shift from Rust to Solidity, then anatomy of a function, modifiers as contract bouncers, building the registry contract, and finally, testing preconditions and logic. Section 1. From Rust to Solidity. A mental shift. Think back to the loop control thinking you practiced in our previous modules. Remember how we were hyper-focused on avoiding unbounded gas consumption by carefully iterating over fixed-size slices of arrays? Well, that same logical control flow is evolving today. Instead of just managing loops, we're taking those checks, those computations, and that repeated logic and wrapping them into beautifully encapsulated, reusable pieces of on-chain logic in Solidity. Basically, we're scaling up our architectural thinking. Section 2. Anatomy of a function, the factory machines. So for a smart contract as a factory, functions are literally the physical machines bolted to the floor doing all the heavy lifting. And of course, every good machine needs an instruction manual, right? In Solidity, that manual is the function signature. Notice how explicit the signature is. The parameter list details exactly what goes into the machine, and the return type shows exactly what comes out. A crystal-clear signature communicates the exact intent and safety of a function, not just to other developers, but to the compiler and ABI parsing tools too. It is literally your contract's public interface. Now, what's really interesting about this is how we can fine-tune these machines using specific dials and switches. Visibility and state mutability. Visibility dials like public, external, internal, and private control exactly who is allowed to walk up and press the start button. Mutability dials like view, pure, or none control whether this machine is actually allowed to alter the factory state or if it's just looking at the data on a clipboard. Getting these settings right is absolutely crucial for both security and gas optimization. Section 3. Modifiers as bouncers. Security guards. So what happens when you have 5 different machines that all require the operator to be the factory manager? You definitely wouldn't want to rewrite that exact same security check inside every single machine's blueprint. That's where modifiers come in. A modifier is exactly what it sounds like. It modifies the behavior of a function. Practically speaking, they're the bouncers standing at the door of our factory machines. They hold reusable precondition logic, they check the rules, and if a caller doesn't meet the criteria, the bouncer turns them away before they ever get to touch the machine inside. This saves us from duplicating code everywhere. Let's look at 2 classic bouncers in action. On one side, we have onlyOwner. This bouncer is checking VIP IDs. He only lets you through if you are the explicit owner of the contract. On the other side, we have validName. Now, this bouncer doesn't care who you are, but he is strictly enforcing the dress code. He's checking the length of the string you're trying to input just to ensure it actually meets our validation rules. 2 totally different jobs, both handled elegantly by modifiers. Section 4. Building the registry. Step-by-step practice. All right, enough theory. Let's move to and see how this builds out in reality. We are unrolling the blueprints for a real contract called the FunctionModifierDemo. We'll do this across 4 distinct phases. First, laying down the storage and skeleton. Second, wiring up our internal helpers. Third, hiring our bouncers, the modifiers. And finally, opening the doors with our public functions. In our first 2 phases, we set our Solidity version to cap 0.8.0, mostly to get those sweet built-in overflow checks. Then we define our state variables, like the public owner and a private mapping of item structs. But take a look at that last point, the underscore ID from name hash helper. The sheer brilliance here is making this deterministic helper internal and pure. It doesn't read state, it just crunches a hash. By keeping it internal, we keep our public-facing API beautifully clean. Next up, phase 3, hiring the bouncers.
Here we define onlyOwner to check msg.sender and validName to check the string length. Both of these modifiers use the require statement to fail fast and revert the transaction if the rules are broken. But you know what the real magic trick is here? It's that little underscore and semicolon at the end of a modifier. Underscore semicolon. That symbol simply tells the contract, hey, if the checks pass, go ahead and execute the actual function body now.
Finally, phase 4, the public functions. We map out exactly which bouncer is assigned to which machine. Add item mutate state, so we apply the validName modifier to it directly in the function signature. Notice we also use calldata for the name string here to efficiently protect storage references. Remove item also mutate state, but it's guarded by onlyOwner. And get item? Well, it doesn't mutate state at all, so it's marked as view and it has no modifiers. Anyone can come take a look. Section 5. Testing preconditions. Verify behavior. Look, a factory isn't finished until the quality assurance inspectors come through. We absolutely need to run specific manual checks and automated hard hat tests to ensure our bouncers are actually kicking out the rule breakers. We try to add a duplicate item to trigger an item already exists revert. We pass an empty string to trigger invalid name length. We try to delete an item from a random account to trigger not the owner. The point is, we anticipate exactly how our contract should fail. So the crucial point is this. Catching these expected reverts proves our preconditions are rock solid. Because we applied the modifiers at the function signature level, the checks run before the function body ever even executes. If a transaction fails the check, it reverts instantly, which saves gas and comprehensively protects our core logic from ever processing bad data. Let's quickly summarize the 3 concrete principles for creating clean, optimized Solidity blueprints. Number 1, make your small helper functions internal or private to keep your public surface lean. 2, always explicitly declare visibility and mutability to document your intent and allow for compiler optimizations. And 3, apply modifiers directly at the function signature to make preconditions painfully obvious and to completely avoid code duplication. You now have the power to separate your validation, your authorization, and your core logic. So here's a question for you. Are you ready to swap these basic bouncers for advanced error handling? In our next lesson, we'll be diving into error handling with require, revert, and assert. But until then, I challenge you. Try taking the contract we just discussed and adding a custom modifier that rate limits how often a specific address can call the item function. Give it a shot. I really hope this breakdown of functions and modifiers gave you a solid, structural understanding of how smart contracts organize their logic. This explainer was made by Forge College. If you want to dive deeper into this subject, check your answers to that challenge we just talked about, or explore other fascinating Web3 topics, be sure to visit forge.college to keep building your foundation. Thanks for learning with me today, and I'll catch you in the next explainer.